Hello, hello, sound test, sound test. Alrighty, we're back here. How is everyone doing? Choo-hoo! Are we? Oh, let me post here. Alrighty. Okay, how's everyone doing? Good afternoon, wherever this may find you. What are we doing today? Hey, Andres, hola. So what are we doing today? We are continuing what we were doing this morning, right? So this morning, as far as I can tell, we did an introduction to what Rhino Common is, and we did some scripting with geometry, simple types. I think, yes, and I forgot to record the intro, so that's why it took a little longer. I think this afternoon we're going to do a few components with vector algebra. So we're going to do a few examples, and then we're going to move on into advanced geometry scripting. So I'm going to teach a few of perhaps the more idiosyncratic ways that Rhino Common has for creating more complex data types like curves, surfaces, that kind of stuff. And I'm going to explain a little bit of how they work. So, and we're going to do examples, of course. Everything is going to come with examples. We're backing everything with examples, which is a good thing. So let me write myself a couple notes here. And then we can get started. So why? All right. So we were here this morning, and I was showing how how I took the work that we did in the previous example, and I put it here in the file that we're going to be using for prototyping our plugin, our Grasshopper plugin. Hey, Nylan, how you doing? It's been a while. And after that, well, what I want to do is a little bit of vector algebra. So we're going to do getting the length of a vector. We're going to get setting the length of a vector. We're going to do unitizing a vector, and we're going to add two vectors together, and we're going to create a plane from 3 points, maybe. I'm thinking about that. And we're going to tween a vector. Okay, that's going to be cool, actually. So, and then we're going to do the cross product. Of course, we can't not live without the cross product, right? All right. Oh, you're in Austin now. All right, welcome. Welcome to the States. So it's still not the same time zone, but yeah, much closer. Much closer now. All right. I wonder if I have a question. So my whole point is teaching Rhino Common. So I'm not going to focus on this series on the geometrical implications of how to do this, but I wonder if it would be nice to at least do it the quick way, or I think I'm still going to do it the quick way, just as an example, but then use the Rhino Common way, actually. All right, I think I'm going to do that. And then for this video, I'm going to record an introduction, which I will do later. So I'm going to start here. Okay, so how are we going to start? We're going to start I'm going to start by this. Okay, I actually don't need to start with this file. Okay, I'm going to start here. So let's do this. Hoo-hoo, hoo-hoo. Beautiful. Let's get started. So, as you already know, over this series, what I intend to do is to slowly, incrementally build up a Grasshopper plugin that I think we're calling it Parametric Chem Toolbox or something like that. It's not going to be very useful because it's mostly going to be components that replicate vanilla functionality, but at least it's going to be a way of teaching us how to build a Grasshopper plugin. And if you remember, I was saying that the first large step we're going to do is that we're going to prototype all of our all of our components in C#. And then at some point, as soon as we learn how to transition to native plugin development, we will just take the code and we will port it, all right? So in the previous exercise, we created a bunch of utility components that just did arithmetic operations, string operations, and numerical sequences. And in this exercise, we're going to create a new category in this future plugin, which is going to be for vector algebra and vector components. And what I have done offline, you haven't seen me do this, is I have taken all the components that we have developed in the videos, in the previous videos, so constructing a point, deconstructing point, constructing vector, constructing vector with 2 points, planes, etc. And I have brought them into this file. I'm going to be building this example incrementally. And what I would like to do in this exercise, as I just explained, is I'm going to add more vector functionality to my plugin, aka I'm going to add more components that do vector algebra. The ones that we have seen in the previous videos are pretty straightforward, creating points, creating vectors, and what they mostly use is basically forms of accessing some kind of constructor that instances new objects of type vector 3D, point 3D, plane, whatever. Okay, in this exercise, I'm going to focus perhaps a little more on things that we can do with those objects once we have created them. Okay, and because you know me already and you know me like the things that I like, maybe I'm going to focus particularly on vectors because I think that vectors and vector algebra is extremely important for computational design. That's probably one of the reasons why they call me Dr. Vector in the first place. Can you hear the background noise? I have someone with a lawnmower just right under my window, which is very unfortunate. Hey, Orlando. Hello, sir. Okay. And the first thing that I would like to do is, given a vector, any vector, I would like to compute some calculations to find its length. So I'm going to create a component that is going to compute the length of a vector. How are we going to do that? Well, very similar to what we have done before. So I'm going to create a component here. I'm going to do this a little faster because we're a little bit more familiar. I'm going to the input is going to be called L, the output is going to be called the input is going to be called V, the output is going to be called L, and I'm going to type the input to be of the type vector 3D. And when I double click here, you can see that I have a very simple component that I'm going to actually copy this because I'm going to be using it a lot, all right? And okay, and then here we go, all right? So as I also said, in this series, I'm not going to focus too much on geometry or explaining geometrical processes. I have other series and other videos for this. So I'm going to go a little bit faster on the geometrical aspect of things. I'm not going to stop too much to explain this. But sufficient to say that there's two ways I could calculate the length of a vector. I could do the square root of all its components squared. So for example, I could say double length is going to be equal to math the square root of bx times, vx times vx, okay, plus vy times vy plus vz times vz. So that would be the way to do it manually, okay? And then I could just output here length, so the value of that variable. Let's see if that works. So I'm going to create a vector, for example. It's going to be this one here. I'm going to I'm going to take it inside a parameter and then I'm going to internalize so that I can just move it around, or maybe I don't even need to internalize it. I just do it like this, and maybe I dim the cable so that it's a little fainter and it's not so obtrusive. And then I'm going to plug it in here. And then I'm going to plug a panel, and it's going to give me the vector length. And just to make sure that things are working, I'm going to calculate for, where is this? The vector length. So I'm just going to use the same vanilla component to see if the calculation is correct. And you can see that, good thing, Dr. Vector knows how to calculate the length of a vector, right? Good thing. All right, I'm just going to rename this vector length, and I'm going to drop the paint bucket so that we have that. Okay, now that would be the way to do the manual calculation. But I'm actually quite interested in teaching you how to do things in the Rhino Common way. So for this series, for example, what I will do is this, I'm going to cancel this. This is going to be the algorithm manual. All right. And then this would be the algorithm Rhino Common. Okay. So here, what I would do is I would say, well, instead of calculating the length of a vector by doing it manually, turns out that vectors have a property called length that I can just read. So for example, if I do v dot, at that point, and you can see that IntelliSense is already pointing at what it thinks I'm going to be looking at, because this thing uses a little bit of AI and Markov chains. So it's already suggesting that there's a property called length that internally computes, makes this calculation, and returns that value to me. So by using this, I can already save myself a little bit of typing and already access the value of that, the value of the length of that vector. What's interesting is that this is very good for us to know as computational designers, but if we are already working in an environment that has a geometry kernel that gives us this kind of utilities, like Rhino Common inside of Grasshopper, or like the Unity engine if we were in Unity, for example, then we can also use that. You know, why not? Okay, so that is how we can calculate the length of a vector. Now, there's a couple other things that we can do, which is we can also say whatever we can also set the length of a vector. What that means is that if a vector has a direction and a particular length, what we can do is we can take a vector and we can change the length of that vector to keep pointing in the same direction, but with a new length. So I'm going to create a component for that. And that is going to be, again, I'm going to create an input. That's going to be V, and that's going to be of the type vector 3D. And the other input is going to be called, for example, L. And that is going to be of the type double. And then the output, I'm going to call it V out. So, because remember, we cannot have V and V as inputs and outputs. We cannot have the same name. Vector length set. I believe, or I'm going to rename this, for example, set vector length. And I believe this is the same functionality that the amplitude component in vanilla does. So I'm going to copy this thing, this vector here. I'm going to plug it in there. I'm going to drop here a slider. I'm going to plug it in here. And we can see that we don't get anything right now. But I'm going to try to see if we keep using the other component, what do we get? And this would be the vector that we get using the vanilla component. Let's see if we can replicate that. So I'm going to copy this panel here, and I'm going to paste it in here. So what am I going to do? I'm going to do the following. I'm going to go here, double click, and then you can see that my inputs are correct. I have the vector, I have a number, and I have the output, which is V out. And you can see that I'm going to do it also again in two ways. I'm going to do the manual way, and I'm going to do it the Rhino Common way. What would be the manual way? The manual way, it is to actually calculate the length of to actually calculate the length of the to actually calculate the length of the vector. And then what we do is we calculate how that length relates to the new length that we want to compute. So for example, what I can say is I can calculate a number called factor, which is a factor is going to be how much bigger or how much smaller we want the original vector to be based on the length that we have right now and based on the length that we want it to be. If you think about this, this is just a proportion. So if it turns out that the L turns out to be twice as big as the length, what we want to do is to multiply the vector by 2. So that's why factor is the length that we want divided by the length that we have. And then the only thing that we need to do is we need to create a new vector 3D new v is going to be a new vector 3D, which is going to have components which are going to be factor times v dot x. So the coordinates of x multiplied by the factor. Factor times v dot y. And then factor times v dot c. Okay? And if that is correct, let's see how we're doing here. Let's see my algebra. And it turns out that, turns out that that approach is the same one. Okay? Now, how would we do this instead of the manual way? How would we do this the Rhino Common way? So I need to double check something because I don't know if length is a set or it only computes, it only gets, so you cannot set it. Okay, so that's something I'm going to want to explain. Square length, can I set is equal is tiny multiply vector by a number, negate perpendicular reverse rotate subtract unitize. So we can unitize the vector and then multiply it by, that could be a way to go. I think I'm going to do that. That's going to be the way to go. Well, first of all, because length, the length of a vector, is a property, so we might be inclined to say, well, maybe what I want to do is I want to say the vector that I have, can I choose length? And then can I just say that length should be equal to the value of L, whatever they're giving me from the outside? So let me also, please, turn this off. So let's see if that is work. If I hit play, you can probably see that the component goes red right away. And why is it that it goes red? Well, this is one reason, but let's see. It says here that the property length cannot be assigned to. It's just read only. What does that mean? Maybe I'm new to Rhino Common, or maybe I'm still figuring out my C# programming. So let's take a look at what that means. What that means is that if I go to the vector 3D structure in the documentation and I start looking for the length property, I can click on the length property, all right? And if I look at this description here, this description is very interesting because what it tells me is length is a property, is of the type double. So whenever I call it, it's going to give me back a double number. But also what I can see here in between the curly brackets is that it's only a get property. What that means is that I can only read from that property, but I cannot write to that property. I cannot just say set, or I cannot assign a value like I have done here, because this is only for reading. It's not for writing. So that's why this line of code is not working. Okay? The option to do here would be something different. What we could do here would be the following. What we could do is we can think about what is the process, what does the process of unitize, what is the process of setting a let me say this again. What does the process of setting the length of a vector means? What it means is that whatever the length it was before, we just want to amplify it to a particular value. So what that means is that one way to do it is typically very easily to just say, whatever the vector is, whatever the length, I don't care anymore. I'm going to reduce it to a length of 1 unit. And then once the vector is reduced to the length of 1 unit, I'm going to scale it up to the length that I'm looking for. So I'm going to multiply it by that length. So how can I do that? So let's see. The first thing that I can do is I can say, I'm going to unitize this vector. And what I'm going to do is I'm going to say, is there any way to unitize vectors? If I do v dot, what you can see is that, first of all, there's a property that tells me whether if this vector is unit or not. That could be interesting, but not for us right now. There's another one here that says unitize, okay? And for this one, I would like to read the description very carefully. It says that it unitizes a vector in place. What it means is that it doesn't return a new vector of length 1. It unitizes the vector that we call this method on. Okay? And one thing that we could notice here is that, in fact, the return type of this method is not going to be a vector. It's also not going to be void. It's not going to be null. It's going to be a Boolean. Why is that the case? It is the case because it turns out that this method returns Boolean, returns true or false, whether if the operation succeeded. Because it turns out that this operation may not succeed. There are cases where a vector cannot be unitized. And one such case, for example, is if the vector has components 0, 0, 0. If the vector is a 0, 0, 0 component, there is no way it can be unitized because we cannot divide by 0 length. Does that make sense? So this is a way to have a method that works and returns two different results. The operation that it does, the unitization, but also a flag indicating whether if it works or not. And this is very useful because sometimes you want to know if the vector unitized or not and be able to respond to those kind of errors. So what I'm going to do is I'm going to unitize the vector. I don't need any information. The vector unitizing is just an operation. It doesn't need any additional information. And then after that, what I can do is I can scale the vector by the factor. Can you hear the lawnmower? Can someone tell me? Hey, Samira, hi. All right, I guess I'll continue then. All right. And then so let's do this. The next thing I'm going to do is I'm going to scale the vector. So I'm going to say, I'm going to create a new vector, which is I'm going to call new v. And I'm going to say this vector is going to be equal to a vector that is the unitized vector v, the one that has already the direction that I care, multiplied by a number. So if I multiply L times v, which is also a Rhino Common operation, multiplying a vector by a number is something that we can't do out of the box. But because of the reasons I explained before, operator overloading, we can do this. And the result of this operation will be a new vector that will be returned, and that will be the original vector scaled by a factor of L. Okay? And then if I now output this new V, let's see if that works. I'm going to hit play, and you can see that it executes and the result is the same. So yoo-hoo! So we were able to unitize this vector and then to scale it up to that particular length. The next thing we're going to do is another operation that is super common and that we have done it. Actually, perhaps we should have done it before, which is unitizing a vector. Okay. So that is also an extremely common operation. So let's see. So what we can do is we can, unitize a vector. So yes, so we're going to take a C# script. We're going to take the input is going to be V, and it's going to be of the type vector 3D, and the output is going to be V out. All right. And then this is going to be unitize vector, and then there you go. And then we're going to take this vector and we're going to unitize it. And sorry, we're going to take another vector that we're going to move here. We're going to unitize it. And then we're going to compare the result with the unit vector, which also I believe is the component that we kind of want to replicate here. So this vector unitize is going to be this one. Okay, so we have done this before, so I'm just going to copy paste a little bit here. The manual algorithm would be Control U to uncomment. The manual algorithm would be something like this. I can calculate the length of the vector, and what I can do is I can divide each one of the components of the vector by the length. So what I can do here is I can create a new vector. I can create a new vector where each one of the components is going to be the original component divided by the length of the vector. So I'm going to say Vy is going to be Vy divided by length, and then factor is going to be equal to blah, 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 divided by length. Okay? And then I'm going to comment this, Control K, Control C, and then you see that the output. And the output is the same. Okay? But if I were to do it in the Rhino Common way, as we have seen before, this, I don't need this, so Control K, C, and then what I need to do is I just need to say, well, I'm going to unitize the vector, and then the result is going to be that I'm going to output that unitized vector. And if I do that, I should also get similar results. So I'm pressing run, and then it's also working great. Okay, beautiful. We have vector. We can unitize vectors, we can calculate the length of a vector, and we can set the length of a vector. What other things can we do? Let's try, for example, adding two vectors together. that one is going to be so simple. I'm just going to basically just do it here. So I'm going to say vector A, type hint, vector 3D, vector 3D for vector B here, and then vector V as an output, and then it's going to be called vector addition. All right. And then what I'm going to do here is that I'm going to take two vectors. So for example, this one and some other vector. I'm just gonna add the two vectors that are the same. It doesn't really matter. So, and then what I'm going to do is I'm going to place here a panel to check the result, and I'm going to compare it to how it would be if I were to do it. It turns out that vectors can be added with the addition component as well, so in vanilla Grasshopper. So let me replicate this. And for this, we're not even going to follow the structure. Oh, what have I done? No. So I'm just going to copy this structure, the manual algorithm, and the so how would we do it manual, how do we do it Rhino Common, and what are the outputs? Okay, so manual, how would this be? Well, I'm going to create a new vector 3D that is called sum, and that's going to be a new vector 3D, which is the component, the x component of a, so a dot x, plus the x component of b, so b dot x. Then the same for y, the y component of a dot a y, plus the y component of b, so b dot y. And then a dot c plus a b dot c. And then the result here is going to be sum. If I now execute this code, something is broken. What just happened here? Name v out does not exist. Yes, I need to, because I was copy pasting, I need to rewrite this, and now I'm going to press run, and you can see that the result is the same. But if I were to do this the Rhino Common way, it would be just as easy as saying vector 3D sum is going to be equal to vector A plus vector B. It's just as simple as that, because Rhino Common gives us this way of adding two vectors together with the plus operation. Okay, I can do that, and then that works. And you can imagine how we can add vectors, subtract vectors, multiply vectors, divide vectors, but I'm not going to do that because, I mean, it's just the same thing, just change the sign. So I'm going to leave that up to you, the viewer, to do it on your own. All right? Something that we can do also quite interestingly is going to be to tween a vector. What does tweening mean? And how are we going to do this? Am I going to do drawings? Can I draw here? Huh. I can actually draw here. Is there any colors here? Oopsies. Okay. Tweening is typically an alias or a nickname that we use for interpolating between two different states. So if we say, can I tween between two different vectors? What we're kind of saying is, imagine I have one vector like this, and I have a second, which I'm going to assume is the starting state. And I have another vector that looks something like this, which I'm going to assume is the end state. Tweening means creating an interpolation between those two. What that means is typically saying that we have a number that defines how far along that interpolation is, And that number, we typically normalize it. We typically say, well, we assume that if we are at interpolation state 0, then we are at the original vector. So 0 means the original vector. 1 means the end vector. And any value in between means a vector that is slowly interpolating over here. So this could be 0.25, this could be 0.5, and this could be 0.75, for example. So what this means is that we want to create a component that we give it two vectors, and that takes two vectors as inputs and takes another number with decimal part from 0 to 1, and then returns a third vector, which is that interpolation between the two states. Okay, so let's do that. So I'm going to, I can keep this here. Why not? It's not, I mean, it's really bad drawing, but why not? Okay, so I'm going to do that. So I'm going to say component, and this is going to be, this is a new vector component that is not available in Grasshopper. So we are starting to add our own opinions here. So A is going to be, for example, not point 3D, sorry, it's going to be vector 3D. B is going to be the other vector, the second one. And I'm going to add a third parameter that I'm going to call T, which is going to be where I am between those two states. And T is going to be of the type double. And the output here is going to be uppercase V. Now, with this, what I can do is let me figure out some data here. So I'm going to do one vector, and I'm going to say, what is the other vector? The other vector, I'm going to take it from here. So I'm going to take this vector, and I'm going to say that the wire display is faint. Okay, and then this vector is going to be here, and I'm going to just drop here a slider. And just to make sure that this works, well, we're going to do it first, okay? And then we will visualize it to see if it actually works. So I got everything working here. So let me then punch some code inside here. So how are we going to do this? Well, turns out that as per the diagram that I drew before, it's actually quite simple. The only thing that we need to do is we need to figure out for the value from 0 to 1 where we are along this virtual line. So what that means is that we basically have to create a line. One way to do this is to create a line between these 2 points and then find where we are along that line. Or we could do this numerically. So we could just calculate the difference in the coordinates of vector A and vector B, and then multiply those by the factor. So let's just do it so let's do the manual algorithm, which is going to be double the difference between the two vectors is going to be Vx minus Ax. All right, and I'm going to copy this 3 times. So the difference y, the difference z, this is going to be y, this is going to be y, and this is going to be c, and this is going to be z. Okay, and then what I can do now is I can create another vector that is going to be the coordinates of this vector, this xy, plus this difference multiplied by how far off we are. So that if we are at 0, the new vector will be exactly the same one. But if we are at t1, the vector will be all the way here because we have added the full difference. So vector 3D tween is going to be equal to a new vector 3D, which is going to be the coordinates of a, so a dot x, plus t times dx. So the difference between the two times the interpolation value. Okay, so I'm going to do it a little fancy here. So I'm going to do a dot x, a dot y, a dot z, and this is going to be dy, and this is going to be dc. And I'm going to close the parentheses here. And then the outputs are going to be v equals the tween variable that I just created. Okay? This will be the manual way of doing it. So how can I verify now that this makes any sense? Well, first of all, let's take a look at the first vector and let's take a look at the second vector. If at 0 we are on the first vector, that should be correct. And if at 1 we are at the second vector, that should also be correct. So it looks like this is working right now, but just in case, we would like to verify this with visually. So I'm going to say display vector, and I'm going to display this one, I'm going to display the second one, and I'm going to display the output. And I'm going to display all of them from the center of coordinates. So you can see that I have vector A, vector V, and the tween one. And if I switch between 0 and 1, you can see that I tween between the original and the target, the original and the target, the original and the target. And as in the previous examples, we can also go out of bounds of this one. So I can set a value of -1 to go beyond, and to go before, and to go beyond. That also works. All right, but that was the manual way of doing it. How could we do this with Rhino Common? Well, similarly, algorithm Rhino Common. There's a bunch of ways that we could do, but I think the easiest one, because we have the two vectors here, is going to be to create a point, to create a line between them two, and to find a point along that line. So I'm going to comment this out, Control K C, and then here I'm going to say, I'm going to create a new line, which is going to be between A and B. But because these are typically points, let me see if this works first. So let me see, this doesn't work, and I cannot convert from vector to point and then tween. Exactly. So these 2 points, these are not points, which is what line needs. These are 2 vectors. So we're going to need to do some translation between these 2. But now that I'm thinking this through, I actually think there's an easier way of doing this with Rhino Common, which is going to be the following, which is going to be, if I have vector A and I have vector V, B, I can find vector C, because C is equal to vector B minus vector A. And then if I multiply vector C times the t value, then if t is 0, then vector is going to be 0, and if t is 1, it's going to be all the way here. So the resulting point can be the addition of A plus vector C multiplied by how far away we are in this line. Okay? So I think I'm going to do that form instead. So let's do that. So what I'm going to do is I'm going to say vector 3D AB is going to be a vector. I'm going to call it C to be consistent with the B is me minus A. And then vector 3D tween is going to be equal to vector A plus vector C times T. And all of this is possible because Rhino Common allows me to add vectors, to subtract vectors, to multiply vectors by scalars so that you amplify or reduce their lengths, to add them together, etc., etc. And I believe this should actually work, correct? I believe so. So let me check this graphically if it works. So this vector here, now that we are going to 0, it is right there. Now that we're going to 1, it is all the way at the other one, and then beyond and before. All right, beautiful. So that's how you can tween two vectors together, for example. Beautiful. And last but not least, let me clean this up a little bit. Okay, let me clean this mess here. And last but not least, what I would like to do is I would like to show you how to compute the cross product of two vectors. Okay, if you are not familiar with this, the cross product of two vectors is a third vector that is perpendicular to the first two and whose length is equal to the area of the parallelogram that they both form together. Okay, why is this and where is this coming from? We're not going to get into in this series. If you're actually interested in that, make sure to check my lecture on my Harvard GSD class, Introduction to Computational Design, and the link should be popping somewhere in the car, or it should also be here somewhere in the description. Okay. But what's interesting about the cross product in Grasshopper is how we actually compute that cross product with Rhino Common, or more specifically, the syntax that we use to do that, which is a little bit special. So let me show you that. Vector cross product. All right, and then this is going to be V. All right. So I'm going to plug in, I'm going to copy paste these two. I'm going to plug them here. I'm going to plug the other one there. And I'm going to compare the result with the cross product, which is available out of the box. So cross product, and you can see that this is the result. Okay. And then you can also see that this component, the vanilla component, gives me the length of the vector and gives me the opportunity to unitize that output if I want it or not. And so if I click here, if I put a toggle, you can see that now the output is not going to be unitized, but if I turn it on, the output is unitized. And then the result of this is 1. This may actually be an interesting thing to implement here. So I'm going to start first with the cross product, and then I will be implementing that unitization. Okay, so this one we're going to do it. I'm not going to get into doing the cross product manually. We're only going to do it the Rhino Common way. So if I didn't know how to do that, one way that I can just find how to do things in Rhino Common, in the Rhino Common API, is just going to the search box and typing here, for example, cross product. And then if I do that, you can see that the first thing that comes up is the vector3d.multiply operator. And this multiplies two vectors together, returning the dot product. This differs from the cross product, so warning, this is not what I want to do. So let me go back to the structure, and maybe I can find a method that is the cross product. I just search for cross, and this is what showed up. So maybe in the search, if I had used one word instead of two, you see, I would have gotten vector3d.crossproduct, which is what I was looking for actually. Okay, so we can see that the vector 3D struct has a method called cross product. So let's see how to use that. I'm going to go here and I'm going to say, I'm going to write the algorithm, and then I might be tempted. Oh, I forgot. Can you see how the inputs are object and object? This is because I forgot to type them. Remember, I forget this all the time, and you'll probably forget it as soon as you get, before you get a bit more practice. So A is a vector 3D and B is also a vector 3D. So now I double click again and this is working well. Remember, you have to exit the code editor to change the types and then come back in. So, okay, so we might be tempted to say vector 3D that I'm going to call cross is going to be equal to A dot and cross product. Wait, there's no cross product method, but hold on. I thought that in the methods, there was something called the cross product. And let me go back to the structure. If I scroll here, if I go to methods, you can see that the cross product is here, just like get type or is parallel. So if I have dot is parallel, why do I not have a dot cross product? Why is this happening? Well, this is one of the funky things, or the special ways Rhino Common is designed. It turns out that the cross product method has this tiny icon here that means that it is static. And the fact that it is static means that instead of being called on instances of objects, so a particular vector A or a particular vector B is called from the global class itself. All right. I'm going to explain that in detail on the next video, what that means, but sufficient to say that the way we do this is that instead of calling it from vector A, what I say is I type the class name, vector 3D, sorry, the struct name, and here you can see that I have another set of methods, multiply, blah, 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 whatever, and one of them being the cross product. So the cross product is, now I can make the cross product of A and B. Okay, and the result is going to be, from this operation, is going to be another method, another vector with that cross product. And then here, the output is going to be V equal cross. Is that true? Am I getting the same result here? It is true. I am getting the same result as in the previous one. Okay, don't worry about that. I'm going to explain on the next video what static methods and what that thing you just saw, which is called the factory constructor pattern, what that means in detail. Okay, and then just to replicate this, I'm going to add another input that's going to be called uppercase U, and it's going to be of the type Boolean, so that it can be only true or false. And I'm going to plug this thing in here. And I'm going to add another output, which is going to be called L. Okay, and that L is going to be the length of the vector. So what I want is to do something where whenever this is true, the vector gets unitized. So that is going to be extremely simple, because now I have U as an input. The only thing that I need to do is I need to say if U equals true, or we know that we can shorthand this. So if we want to, if unitize is true, then what we can do is we can take the vector, which is cross, and we can unitize it. And we call the method. And that's it. Because we know that unitize is going to unitize that vector in place. It's not going to return a new vector. It's just going to affect the vector that it is called upon. And now for L, we can say, let's just output here the value of the length of this vector. Okay. I can do that. And then you can see that now the vector has been unitized, same value, and the length is 1. And if I turn this off, then the vector is normal, and the length is also whatever that is. All right. Okay, so I think that was it for me for vector algebra. Let me just move this over here and make things a little cleaner and tidier. and I'm going to make this another group, and probably as soon as I make this, I turn this into a plugin, I will have a separator here. Like, you know, you have these separators here. I will probably do that for these components here, and I will teach you how to do that. Okay, and I think that's it. That covered some of the most basic vector manipulation and vector algebra that I'm going to cover in this example. In the next video, what I'm going to do is I'm going to cover how to create and manipulate more complex data types like curves and B-reps, for example. And we will do another exercise with a bit more complex generation of those geometries, like lofting, like sweeping, or like interpolating a curve through a sequence of points. Okay, beautiful. Thank you very much for watching this video. If you liked what you saw, maybe click the like button, subscribe to the channel, keep watching the videos in this series, or however your form of showing some gratitude or spreading the word of the work that we do here, however you want to do that yourself. Okay, thank you very much. See you on the next video. All right, I think the guy with the lawnmower left. Whew. I'm really dry. Okay. So vector components, and none of these, because they're all vectors, they don't really have visualization, but it doesn't matter. Okay, and these are the comparisons. We also don't care about this. All right. How's everyone doing? How are you liking this so far? Oh no, wait. So, okay, here, there you go, and there. Just a little bit of cleanup, because otherwise my OCD is not gonna let me sleep well tonight. And there you go. I think that's enough. Oh, oof. Saturday afternoon, huh? I'm a little beat. Okay, so vector components. Add link card to the vectors GSD vector. Okay, and I need to record the introduction. I forgot. Hello, this is Jose Luis here at Parametric Camp, and welcome to this new hands-on exercise on the course Advanced Development for Grasshopper. In this exercise, we're going to be developing a bunch of Grasshopper components that are specifically designed for vector operations. So, as you saw in the previous video, we have construct point, construct vectors, lines, and plane. But in this one in particular, I would like to teach you, for example, how to unitize a vector, how to calculate the length of a vector, how to set the length of that vector, how to add two vectors together, how to create the cross product between them, and how to tween two vectors and create an interpolation between them. Okay. My purpose in this video is to not get too deep into the underlying geometrical concepts behind these operations, but mostly teaching you how to use Rhino Common to perform these operations and how to learn from the documentation how to do them. Okay? So it's going to be hands-on. We're going to do it together, and it's going to help reinforce everything that we have seen before in the previous videos. So let's talking and more coding. Let's crank some vector algebra components. Hold on, I need to pick up a call. Hold on, I'll be right back. 1 minute. Just 1 minute. All right, I'm back. Sorry. Okay. All right. More. So what is next? The next thing is going to be, well, we have vector components. I'm going to save this and close this. We have, what else do we have? We have advanced geometry scripting here. I have. Take a closer look at more advanced geometry example. Oh. Creating curves, surfaces, subdivisions. Okay. Go for the blend, point for blend intersection, continuity, tangency curve. Create from corner points. All right. Can you? So, okay. Okay. Vector, 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 curve class. I'm going to point to pcamp and playlist. Static members. Interesting. And here I explained. Oh, there. Ooh. Okay. Oh, okay, I think this. Okay. Maybe this is a good example. So, static members here. Okay. Okay. Mm-hmm. All right. Okay. All right. So how are we going to start? For this video, I don't need introduction. I'm not going to need introduction. Um, okay. Mm-hmm. And I guess it's not. Uh, I'm not sure this is any good, really. Mm-hmm. What can I do? How can I show something that relates to the pattern? Uh, is there any nice diagram? Eh, I mean, at least this looks nice, but but I'm not sure there's a good explanation here. This is also quite technical. I wonder if we are just going to tiptoe over it. Okay. All right, so I'm just going to start by saying that I'm going to take a look at the previous example. So that was going to be okay, and scripting with geometry. All right, and then we're going to use this. Okay. Mm-hmm. Mm-hmm. Mm. Okay. All right. So let me start here, perhaps. I'm going to start by explaining that the vector and all these simple classes, we use constructors to create them, and that's great. But for more complex types, I have so much information. Providing all the information from start, it's not really. So, and I'm going to start here. Okay. All right. Mm-hmm. Hello, this is Jose Luis here at Parametric Camp, and welcome to this new video in the series Advanced Development in Grasshopper. In this video, I would like to talk specifically about the topic of advanced geometry or more complex geometry when we are scripting inside of Grasshopper. And the topic that I want to cover is the difference between what I referred to in the previous videos as simpler data types or those which are typically under the structures types. So for example, points, vectors, lines, planes, which are like represented with very simple numerical components, as opposed to the more complex data types that are, for example, B-reps, curves, meshes, that contain a lot of information and a lot of functionality. And the difference that I want to establish here is because if you remember from the previous examples, when we created points or vectors or planes, it was actually very straightforward. What we used to create points, for example, in 3D was a constructor that takes 3 values, for example. When it comes to vectors, we also use a constructor that takes also 3 components, although it could also take other forms. For example, when we create planes, we use a constructor that takes a point, 2 vectors, even though we have other options like 3 points or the 4 components of, or when we create a line, for example, we can create a line by just, but you can create a line by just setting the line between 2 points. And this is because all these objects, all these types are so simple that by providing simple units of information like numbers, points, or vectors to the constructor, we can give these objects enough information to create those structures. For example, here in vector, you can see that the constructors, there's 4 types, one that takes a point, one that takes a vector, one that takes another vector, and one that takes 3 numbers. And that is all that we need in order to create a vector. However, when we, for example, want to create curves and V-reps, which are more complex, turns out that they require so much information that if we were to manually have to compose all the information, first of all, it would be super tedious, but on top of that, because it's nerve geometry, it turns out that the generation of all the mathematical properties that we need to fully represent a curve or a B-rep is also quite technically challenging and at some point kind of very difficult to do. So that's why it turns out that curve and B-reps and other complex data types in Rhino Common exhibit a... I got lost. I don't think that's what I wanted to say. I think I was saying things in a different order than what I actually wanted to say. So let me rewind. I want to catch the all right, I don't know how to do that. I don't know how to catch just the cover of the video. Anyway, I think I need to start this video over again. All right, so I'm going to start over again the video. I'm going to start the video over again. Hi, this is Jose Luis here at Parametric Camp, and in this video in the series Advanced Development in Grasshopper, what I would like to do is I would like to introduce you to the generation of more complex data types like curves and B-reps, and very specifically to the more idiosyncratic patterns that Rhino Common uses for the generation of those particular more complex data types. And why am I saying this? Well, if you remember from previous lectures, you remember that I was discussing how, in general, Rhino divides simpler data types into using structures. So, for example, structures are used for points, for lines, for vectors, for data types that have very simple numerical representations, like 3 numbers, 4 numbers, a point and 2 vectors, something that can be very easy to represent. However, classes are typically used in Rhino Common for more complex data types like curves, B-reps, meshes, objects that have a lot of information, a lot of functionality, and that are a bit more heavyweight. And this is because when we generate, for example, simpler data types like vectors, you remember that we were using simple constructors where we passed initial information, like the 3 components of the vector, and then we created an instance of that object. That is the same for planes, for lines, for points, and we can see that if we go to the vector 3D structure, the constructor has several overloads that allow us to give it different types of information to create that instance. Unfortunately, or well, I don't know if that's some, actually, I take that back, the unfortunately. Differently, curves and B-reps, because it turns out that they have much more information, we cannot use simple constructors to create curves or to create B-reps. If we go to the documentation of the B-rep class, for example, we can see that it has 2 constructors, one to create an empty B-rep and another with this weird thing called serialization information and streaming context, which we can't even access because it's protected, and I can see it from the icon right here. Whereas the curve class, for example, doesn't even have any constructor available. This one, I cannot even use it because it's also protected. So if that's the case, how can I create curves and B-reps? And also, why do I not have constructors? It turns out that I don't have constructors for these classes because if I were to have to provide all the atomic information that I need in order to have a fully fledged first citizen curve object or B-rep, because they are NURBS geometry, the properties that they need, all the control points, all the knot information, the domain, all of that, it's very tedious and mathematically intense to generate. And not very honestly, it escapes my own personal comprehension to how to do that in many cases, right? So, and the same for B-reps. We cannot generate all those numerical representations manually. As opposed to that, we're actually used by using Rhino, we're used to other methods of creating curves and creating B-reps, which is by using third-party information or using methods of modeling that lead to the creation of these objects. So for example, I can create a curve by interpolating through a sequence of 10 points. Turns out that the math behind that operation is kind of complex, so it is a little hidden behind the scenes inside of the Rhino Common geometry kernel. Same for B-reps. If I want to create a B-rep as a loft between a series of curves, the math behind that it's pretty intense, and doing that manually ourselves, if we knew how to do that, then basically Rhino as a modeler would not have a lot of commercial value, right? So that's why all of that goodness is hidden away from us. But Rhino gives us interfaces, methods, and ways to generate B reps and curves from those types of source information. So particularly, what I would like to teach you in this video is the two main patterns that are a little specific to Rhino and which are used to create these types of more complex information. And the first pattern that I'm going to describe to you is what's typically referred to as the factory method in the C# programming language. What that means is that the factory method pattern is a design pattern that is used very often for the creation of new instances of objects, but instead of using a constructor, the factory method typically uses what's called a static method in the class. Let's take a look at what that means. What that means is that, for example, let me create a new file, and let's say that I want to create the folder, the component, which is going to be blend curve. Okay? There is a component that takes two curves and that blends them together. That creates a third curve that is the blend between the two with a particular continuity. And let me actually put here a little bit of data. For example, this one here, right? And these are going to be the two curves. So I'm going to take one curve as an input. Then this is going to be the other curve as an input. And then I'm going to plug these two together. All right. And you can see that the component has generated this interpolated curve that is blended and it maintains curvature and tangency at the two ends. All right. So here, for example, I have this slider that I can use to control the type of curvature. 2 means the type of tangency, the continuity. 2 type means curvature, 1 means just tangency, and 0 means position, which ends up being just a straight line. Okay? So how could we generate this curve using Rhino Common? Well, if I go to the curve class, you can see that the constructor, there's no constructor with two curves and an integer for the continuity. We don't have such a thing. However, if we scroll down all the way to the methods, we will see that at some point we reach a section that has a lot of methods that are called create arc blend, create blend curve, blend with continuity, create Boolean difference, create Boolean intersection, create curve 2B, create fillet, create curves, create matching curves, create text outlines, create tween curves. There's a lot of methods that are useful for creating curves, all right? And each one of them, depending on how they create these curves, they use different inputs. So this one takes two curves, this one takes, for example, a list of curves, this takes a list of curves and a plane, etc., etc. Okay? Now, what I want you to notice is that all of these methods have this S icon here on the documentation. So for example, if I click on create blend curve, I can see that in the documentation, this tells me that I can create a curve blending between two existing curves. And the documentation tells me that given a curve, given another curve, and given this other thing called blend continuity, which I will explain in a second, the returning type is going to be a third curve. So this is matching where I am, so I kind of like this. It's just that there is an additional thing that I need to keep in mind, which is that this method is static. And this is the difference, and this is where the pattern kicks in. The idea is that Rhino uses static methods for the creation of more complex geometry. And what does that mean? It means that instead of using constructors where I pass this information, it designs particular methods, but these methods do not belong to instances of classes. Sorry, for example, they do not belong to instances of particular curves. I cannot create the blend curve calling it on curve A or curve B or any particular curve. The only way I can call this method is because it is static. I need to call it from the class itself. So the class itself, the overall class, will have these methods which do not belong to any particular curve. They belong to the class in itself. And the only difference is that the syntax will be a little different. Instead of typing a dot create blend curve, I will type curve, which is the name of the class, dot, and create blend curve. I know that this is a little bit confusing, but let me show you an example of that. So I'm going to try to replicate this component. I'm going to say the input is going to be A, this other input is going to be B, and then and this is going to be of the type curve, which I'm kind of hiding here, and B is going to be of the type curve, okay? And then this is going to be the blend, for example. And I'm going to input this curve here, I'm going to input this other curve, and I'm going to turn this off to see if things work out. Now I am going to double click here. I'm going to have my development here. And then what I would like to do now is I'm going to design the algorithm and I'm going to design the outputs. So the algorithm is going to be that I want to create one curve that is the blend between the other two. So I'm going to create a curve that I'm going to call blend. And here, maybe before I would have been tempted to say new curve from A to B and with 2 as continuity, right? But if I do this, this doesn't work because the geometry curve class does not contain any constructor that takes these arguments, okay? Remember, the class, the curve class, does not have those constructors. Instead, what it has is the whole create blend curve method. So maybe I may feel inclined to say, okay, well, instead of this, if there's no constructor, then maybe what I need to do is I need to say a dot create blend curve and then a b, but this also does not work, okay? And it doesn't work because create blend curve does not belong to any particular curve or A or B, it belongs to the class. So the correct way of calling static methods is by calling them from the class itself. So what that means is that I can type curve, which is the name of the class, dot, and as I type dot, you can see that right away I start getting access to a lot of those static methods, okay? A lot of those static methods that give me additional functionality that doesn't belong to any particular object. So for example, I can choose create blend curve. You can see that it's static here, that it takes 2 curves and a blend continuity object, okay? So I'm going to do blend, create blend curve, all right? And then the inputs are going to be A, then it's going to be B, and then it's going to be an enumerator that describes what position, what tangency do I want between them. So for example, I'm going to scroll down and say that I want tangency continuity. And if that's the case, then the output blend should be equal to, I want to output on the component this variable that I just created. And if I do that, now things work out. And then you can see that as I click here, this nice curve is getting highlighted. And you can see that it's not exactly the same as the one we have in here because I chose tangency, which is number 1. Okay, so if I were to choose here, if I were to choose blend continuity dot curvature, then I would be equal to option number 2 here. Okay, so that I just described, this idea that you can create new objects of a particular type by using methods that are static and that don't belong to any class and to any object, but belong to the class itself. This idea is what's typically referred to as the factory method pattern. And I'm explaining this here in this video because It's a pattern that is extremely common, in particular inside of Rhino Common. All right? Rhino Common, right? So here we are, and that's the reason why I'm going to explain this. I'm preparing what I want to explain on the next video, okay, which is going to be the same thing, using a B-rep, creating a B-rep from 4 points. Okay. So let me show you another example. All right, so how are we going to, yes. So here I'm going to hide this. And I'm going to hide this here. All right, and I'm going to save this file before I lose it. And this is going to be called 3.3 Advanced Geometry. Okay. Maybe it's not advanced geometry. Maybe it's more like factory methods or such. I'm not sure. We'll see about that. Now let me show you another example of a factory method for constructing new objects. When it comes to B-reps, for example, there's this component that is called 4-point surface, which creates B-reps from 4 points. So for example, I can give it these 4 points and it's going to create a B-rep between them, okay? So I have taken 4 points from Rhino, I feed them into the component, and here I have created a C# script component that takes 4 inputs, A, B, C, and D, and that for each one of them, I have typed them as 0.3D objects. So now I have here in my component, I have 4 inputs, which are the points A, B, C, D, and I have the S output. All right. So I'm going to now find a way to output here a B-rep that is formed from those 4 points. So how could I do that? Well, the first thing we do typically is that we go to the documentation, B-rep class, B-rep, we look at this, we see all the properties, it has curves, faces, edges, whether if it's manifold, whether if it's solid, etc. There's a bunch of stuff. In general, the methods that have just the purple box, those are instance methods, so you can call them from particular objects. And the methods that have the S, those are static methods, all right? And you can see that we also reach this new section that called create. And then you can see that there's a lot of methods: create baseball sphere, create blend shape, create Boolean difference, create Boolean union, chamfer, contour, curvature analysis, fillet, create from box, from corner points, from lofts, from spheres, from sweeps. There's a lot of creating components for B-reps because there's many different ways to create B-reps. You see the list just keeps going and going: create thick pipe, create trim surface, and you can see how invariably all of these were static components. All right. So what I'm going to do now is that I'm going to use, for example, this one, create from corner points, to use that to create a component to create a B-rep from those 4 points. And you can see that if we look at the syntax, very straightforward. This is the method name. These are the 4 input points that we need as arguments. And we also have a tolerance value that we need to work with. You can see that the return type is a B-rep, and you can see that this method is static. So I need to call it from the B-rep class. So how are we going to do this? I'm going to say B-rep serve is going to be equal to not new B a construct. So that Boolean curvature. Oh no. Does anyone know where did the audio cut? Because I'm gonna have to record that again. Stupid microphone. I really disliked it. It's always the same stuff. Does anyone know where the audio cut? At which point did we lose audio? Uh, that far away? Oh no. When I started coding, oh my God. Okay. Okay, so all right, so let's do this again then. Ah, that's so annoying. But Andres, did I get to explain this create from points? Did I explain that? Did you hear me that? Or did I just and was it just when coding, or do I need to repeat this part again? It's very hot here today. Oh. Hmm. Okay. I don't know. Oh, I really lost track of this. So how can we? I think this part was okay. Somebody else could say something. Yeah. Okay. Thank you, Andres. Um, um, let's just start over again. It's fine. After creating the C# component. So wait, so Michael, so none of the explanations, so none of the explanation. I'm just gonna start over again and with that part. I'm just gonna start over again and we can re-record this. Which means that I was here and I was here. So I'm just going to start over again, okay? It doesn't matter. Create blend method. All right, so I'm going to explain this again. Okay, let's see another example of using factory methods to construct new instances of objects, of geometrical objects, of geometrical objects. Starting over again. Okay, so let's see another example of using factory methods to construct new instances of objects here in Rhino Common. So we have seen how to do it with curves, but here I have another example where I have created a B-rep, a surface, out of 4 points that I am loading in from Rhino. So you can see I can move these points that are in Rhino and are referencing Grasshopper, and then I can create a B-rep from the 4 corners, okay? Now, how could I do that? Well, if I were to write, and here I have an empty C# script component where I have plugged in the 4 inputs, I have renamed the inputs, I have renamed the outputs, and I have made sure to right click and set that the input type for each one of them is point 3D. So once I have this, now the question is, how can I create inside here in the code, how can I create a B-rep just working with 4 points? We have the same problem that we had here before with curves, and is that if we go to the documentation, which is typically the first place where we should start, if we go to the documentation, we can see that we don't have constructors with 4 points or with curves or whatever. What we know is that if we keep scrolling, if we go to the properties, we can see all the different information that we can retrieve from BREPs. We can see that we have a lot of methods that are part of BREPs, and in general, you can see that this icon, the purple box, signifies that a method is an instance method, which means that it belongs to particular objects. So I can call it from a particular BREP. However, the ones that have the big S are static methods, and those are the ones that can be accessed from the class. So if I keep going down, you can see that at some point I reach this create section where there's a lot of methods that are called create something. Create baseball sphere, create Boolean difference, create Boolean union, create transfer, contour, fillet, create from box, create from cylinder, from loft. We're going to use this later in the example. From sphere, from sweep. There's a lot of different methods, and the list keeps going on and on and on. Because Rhino gives us a lot of really interesting methods to create BREPs. And you can see that invariably, all of these are static. They all have the tiny s. So what that means is that they're all called directly from the class. And in this case, for our example, I think that the create from corner points is going to be particularly useful. So I'm going to click here and I'm going to read the documentation and notice how this is pretty much what I expected. I have a method. The method takes 4 points as inputs. It takes an additional argument, which is the tolerance. It returns a BREP. So that's what we get in result. And the method is static, which means that we don't call it directly from any BREP, or is also not a constructor. We call it from the BREP class itself. Let's go and take a look at how this works. So yeah, I am back in Grasshopper. And then here what I say is I'm going to create a BREP that I'm going to call surface. And this is going to be not a new BREP that I pass A, B, and C. No, because this is the constructor way. So we have seen how the way this works in Rhino is that we use the factory method. So that means we call the class BREP. That's the name of the class. We use dot. And then you can see how immediately we get all this autocomplete with the different factory methods that we can access, the static methods that are part of the BREP class. I can keep scrolling and you can see that I reach at some point create from corner points, which is what I want it to be. And so I do that. And then here I can say A, B, C, and D. And then you can see that the fifth input is going to be some kind of tolerance. We have not seen yet how to get tolerance from the document that we're using. So I'm just going to type some small value, okay? All right, and then once we have that, we say the output S of the component has to be the value of the variable surface. And when we do that, I should be able to hit OK. And you can see that this is very dark red, and that's because the two surfaces, the vanilla one and the C# one, are overlapping with each other, which is a very good sign. It means we did a good job. All right. Beautiful. So what's the bottom line? First thing that I want to teach you in this video, whenever you want to create curves and BREPs and meshes and complex data objects, very likely when you go to the documentation, don't look at the constructor. That's not how we typically do them in Rhino Common. You typically need to go into the methods section and look for static methods to create these data types. All right. And also very helpful for you is to be able to see what kind of processes you can use to generate BREPs. Just read the documentation, read the names of the methods, read their descriptions, and it will give you a really good idea about the options that you have for creating surfaces. Okay. And also a friendly reminder, in our other playlist, the Learning C# playlist, there is an episode where we discuss static members and we discuss how to create classes that have instance members, static members, the difference between them. So if you want to hear about this topic again, make sure to go and check out this video. A card should be popping somewhere up there, or maybe the link is in the description. We will see about that. All right. Wonderful. And with this was the first pattern that I wanted to teach you. In the second one that I want to teach you in this video is going to be the out modifier in input parameters. You are so right, Michael. It's been a long day. So I want to finish this video and we're going to wrap it up because it's been a lot. Okay? All right. So okay. So all right. Okay, so I am going to create a third point here. I'm going to bring that point here. Plane. And then I'm going to create an intersection that is going to be the surface and the plane. And we can see how I move this up or down. Okay. So how are we going to do this with computer code? So I'm going to input B, I'm going to input, so this is going to be P, all right, and this is going to be C, and it's going to be PTS. All right. Oh, I need to find the intersect method. Huh. Intersect, intersection, B, rep, and plane. Here with an infinite plane. Okay. All right. Okay, so for example, let's take a look at other types of geometrical operations that we might often do. And let's take a look particularly at the kind that when executed, they deal with a lot of information and they want to give us back a lot of different information and in different types. So for example, let's say that we want to, for the surface that we created before, that we wanted to compute the intersection of that surface with a plane in three-dimensional space. So what I have done here is that to the surface that we had before, I have dropped this component that is called intersection between a B-rep and a plane, all right? Or otherwise called a section. And then I have fed the original brep, I have fed it a horizontal plane that is controlled by a central point. So if I move the point a little bit up or down, you can see that where those intersections are happening is changing, all right? And another thing that is worthy of noticing here is that the output of this component is two different things. One, it's a family of curves, but at the same time, it has another input, which is a set of section points. There are certain instances where, depending on the geometry of the brep and the geometry of the plane, the intersection may actually be just one point, all right, instead of curves. So this is something that we have to take into account or into consideration. So I have created here a C# script component that has symmetry with the vanilla one. So the input is B, the other input is P for the plane. I haven't typed them, so I'm going to right click here and set that this one needs to be of the type brep, which is right over here, and P needs to be of the type plane, which is right over here. Okay, and then I'm going to feed it the brep, I'm going to feed it the plane, and I'm going to plug in here a couple panels. So this panel here, and then this other panel here for the points, and then I'm going to copy these two here, and I'm going to do it here and here. Okay, so right now we are ready to write our algorithm to generate the solutions and another section for the outputs of this component. Okay, so we want to create an intersection between a brep and a plane. Where do we even start? What is that in Rhino Common? Well, turns out that intersections are a little weird in Rhino. For some reason, they are not part of the geometry namespace. They are in a different namespace. So they're actually in a They're actually in a different namespace that is inside of geometry, which is called intersect. Okay, so if I go here to Rhino Geometry Intersect, you can see that intersect has a bunch of classes, structures, enumerators, etc. to generate static intersections. And then intersection is a class that provides static methods for the computation of intersections. We've already seen that before, what that means. This is just a big class that the only thing that it does is it has static methods to generate these kinds of intersections. And we can see that there is one among the first one, which is brep and a plane. So it intersects a brep with an infinite plane. If I click here, I can see that this is starting to look familiar. So brep plane, the input is a brep. It's a plane, there is a tolerance, and it is a static method that returns a Boolean type. It doesn't return curves or it doesn't return points, which is kind of strange, correct? Now, the problem here is threefold. The problem is that this method is actually quite nicely designed because it is able to give us back the curves, the points, and a Boolean flag that tells us if the intersection succeeded or not. The plane might be somewhere away that doesn't intersect the brep at all, and then the result might be false. And this is very good to know if we want to do conditionals like, oh, if the intersection worked out, do something. If it didn't, give an error, warning, etc., etc. So that is very nicely. The problem is that in C#, when you create functions, functions can only return one data type. So they can only return a Boolean, or they can only return an array of curves, or they can only return an array of point 3Ds. And that's it. They cannot return three different things. That's just not part of how the language works. So what is a workaround to do to this situation in situations where a method wants to return a lot of different things? The workaround to this is another pattern that Rhino Common in particular uses a lot, which is using out modifiers for certain input parameters. What does that mean? It means that before we call this brep method, what we do is we generate variables, empty variables, that are going to be containers for the information that we want to retrieve back from the method. And then what we do is, when we call the brep plane, as part of the arguments, we also pass in those variables that we just created, which are empty, they have nothing, because what we want is for the method to fill them in with the intersection curves, or with the intersection point, or with whatever information we want to get back. And what's interesting about this method, this pattern, is that we don't have any limit about how much empty containers we can provide to a function to get filled in with data. And we also have no limitations about the types of them, because this can be an array of curves, this can be an array of point 3Ds, and the method can still return something. It can still return true or false, in this case, for example. So that's why this idea of modifying some of the inputs to have this out modifier to indicate that this is not information that the method needs in order to work with it. What this input is basically a handoff of an empty container to be filled in with information by the method and to be then sent back to whoever gave it to the method. Does that make sense? Maybe it doesn't, and that's fine, because it's a really strange way of explaining this. But let me show you an example of how to do this. So we said that we're going to call the brep method, which is static, and it lives inside Rhino geometry intersect. So because this is a very okay. So I'm going to write it here. So we're going to start by saying we're going to find that method. So I'm going to start typing Rhino dot, and you can see that I find the geometry namespace dot intersection. You can see intersect, and then dot, and then intersection is the class that contains all those methods. If you ask me, I find that all of this is a little strange. I don't know why the intersection is just not in geometry, and that's it. But it is what it is. And then when I hit dot, you can see that I get access to all the static intersection methods. And I get here this one called brep and plane. All right? So brep and plane is asking me for a bunch of things. It's asking me for the brep that I want to use, that I want to cut. So that's going to be B, the input. The plane that I want to cut with, that's going to be P. A value of a tolerance, and for the time being, we're going to use just a small number, all right? And then it's asking me for the out parameters. It's asking me for an empty container to store the section curves, and another empty container to store the intersection points. How can I do that? Well, a way to do this typically is to do that beforehand. So what we can do is we can say, I'm going to need an array of curves to store those intersections. So I'm going to create an array of curves, right? And I'm going to call this sections. I'm also going to need an array of points, which are going to be the intersection points. So I'm going to create here a new variable, which is going to be an array of point 3Ds, and I'm going to call this intersects, okay? And then, once I have those empty containers that have absolutely nothing, those are the ones that I pass to the method. I'm going to hand off my sections variable, which will get filled in with data, and I'm going to pass in my intersects variable, which will also get passed in with data. All right? And hopefully this will work. So whenever this method gets called, this is the input data, this variable gets filled in with data, this variable gets filled in with data, and now we can use that to output the results. So the output C should get the result, whatever is stored inside of sections. And remember, I can output arrays. That's not a problem at all. And the output PTS should have whatever is now available inside of intersects. Correct? Let's see if this runs. Boom, I got an error here. So what is the error? The error is that, oh, that's that I do this all the time. Let's take a look at the error. The error is the argument 4 must be passed with the out keyword, and the same for argument 5. This happens to me all the time. So what I need to remember is that this needs to explicitly have an out modifier that I pass in here, because otherwise the component gets confused. It thinks that it's actually information that it needs. All right, so I'm going to hit run, and then I hope that this works now, and I can see that I have two planar curves, and I can see that these two planar curves are overlapping with these ones here. So you can see if I turn them off, everything gets turned off, and these are the intersections. So it looks like it's working well. All right, this is great. Okay, this is working pretty neatly. I'm going to plug in something here to the out component, because something that I want to highlight is that this is working great, but this is not very elegant, because if you remember, the brep method also gives me a return type, which is of the type Boolean, which tells me whether if the intersection succeeded or not. So what I can do is that this is actually really important information. But in my case, in my code, I have not dealt with that at all. There's no way I am reading or I'm using that information that is coming back from the brep plain method. So something that I can do is I can say, let me create a value, a Boolean variable that is going to be called success, and it's going to be whatever this method returns, that Boolean that it returns. Remember, these two have their own way of working, so they get filled in whatever, but the return type is a Boolean value. And then here, what I can do is I can say, if success equals true, or we can shorthand this to success, then we can print on the console intersection worked. And then otherwise else we can print intersection failed. All right, and let's see if this works. So I'm going to hit OK, and you can see that right now intersection worked, and I have the point, so I'm going to start moving it up a little bit, up a little bit, up more, up more, up more, and all the way until I leave the surface. And at that point, you can see that the intersection still worked, but it just has nothing on it. Okay, it's just giving me no intersection whatsoever. And this one is actually, and this one is now failing here. All right, this one is failing, and this one is failing. Wow, that's pretty nice. So we are catching the same errors here. All right, neat. All right, I like this a lot. Okay, so this was great. Remember the out parameter and the idea that we may need to use some methods where we need to predefine variables that will get completed with values that are generated inside of the function and that are referenced with the out modifier. This is a very common pattern that we will find in Rhino, specifically when we use methods that deal with a lot of information or don't want to give us back a lot of information. The intersection ones are a typical example. Subdivision components are also a very typical example. All right. If you want to learn more about the out parameter, you have the Microsoft documentation, but also here in our Learning C# playlist, I have an episode as well where we discuss out parameters in function arguments, and you can learn a bit more about that, technically what that means. All right. Oh, look at me. It's this guy here. Boop, 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 boop. I poke your nose, poke your nose. Okay, so that was advanced geometry types inside of Grasshopper. And I think what I'm going to do next is that the next video is going to be another hands-on exercise where I'm going to go over more examples of factory methods. So creating lofts, creating sweeps, creating interpolated curves. And I'm going to do more of this other example, using methods that require inputs with the out modifier. Okay, so let's keep building up our plugin. with some nurse geometry components using all these techniques, okay? Thank you very much. If you like this video, maybe hit the like button or subscribe to the channel, or just say hi in the comments. That's also fine. And see you on the next video. Thanks a lot. Bye-bye. All right. And I'm going to remind myself. Okay. All right. I think we're done with this. Thank you very much, Michael. I appreciate that. And with this, I am going to call it, I'm calling it a day, I think. Because I need to run a lot of errands now. So, where is this? I don't even know where we are anymore. 3.3, there you go. I'm going to save the file. I'm going to save this file. How are we doing, folks? Are you enjoying this? Thanks a lot for holding on. And thanks a lot, Rolando. I hope you found this useful. And I'm shutting everything down. Of course, I did like half of what I wanted to do today, but you know, sometimes things get complicated. Sometimes you have to sell furniture halfway through the live stream. Sometimes the microphone fails. You know, this is what happens with live shows. All right. Thank you, Sebastian. Beautiful. Thank you very much, everyone. I appreciate that you're here. I'll see you on the next live stream, which I'm not entirely sure when it's going to be, but just stay tuned to Discord, social media, Instagram, the Google Calendar, all of that stuff. Okay. Thank you very much. Bye-bye.